Okay, so this is joint work with Adi Botea. Well, as you all know, relaxed plans heuristics are computed by finding a plan in a relaxed instance of a problem where you ignore deletes, and they are a very effective and essential component. And the heuristics are based on relaxed plans are a very effective and essential component of many planners, including those there. And for the ones who were here at the previous session, saw that they're still really very good for satisficing planning. The use of relaxed plans in satisficing planning is multiple. It's not only used as a heuristic estimator, but also there's some other uses. For example, the planners that exploit helpful actions, preferred operators, or several versions of those, and also look-ahead macros. And for those who are familiar with the YASP planner, this is what actually I mean by look-ahead macros. I'll go over that a little bit afterwards. But relaxed plan heuristics are not the holy grail, and it turns out that there are very simple problems that these heuristics are not able to tackle well. So here I'll show you one. This is a storage domain which was proposed for the competition in 2006. It was meant to be a very simple domain, even if you look at the description that I think Alfonso, some of the people that designed this, they say it's actually a very simple domain. The interesting thing is supposed to be the preferences that we put on top. But it turned out that even if you don't consider the preferences, it's really hard. So the problem is the following. You have to move crates from containers to depots. And the goals are just that, move crates from containers to depots. And although it's simple in theory, and you can, at least non-optimal solutions are simple to compute in theory, it turns out to be not that easy. For example, instances 20 to 30 cannot be solved by most planners, including FF, Fast Downward, Llama, and maybe others, YASP, for example. Okay, so high-level reason for this is oversimplifications. There are some things that are oversimplified in this domain that are key to the performance of the planners. And the case turns out to be pretty bad. And I'll tell you why afterwards. Okay? So the motivation for this work is to investigate the effectiveness of what I will call here, in intuitive terms, not so relaxed plans. Okay? So there will still be relaxed plans, but hopefully not so relaxed. And by being not so relaxed, they will be respecting some of the information of the deletes. So the contributions of the paper will be we define an optimization problem in which feasible solutions are relaxed plans. So we're now treating relaxed plan computation as an optimization problem. And the objective of the optimization problem will be minimize the number of conflicts in the relaxed plans. And intuitively, those conflicts are going to reflect the fact that there's something wrong in the relaxed plan. Okay? And by minimizing them, we're trying to get something better. We will propose a greedy algorithm for solving the optimization problem. We'll explain why we need to do this and why this may not be the best thing to do. And we define a new look-ahead strategy. So in developing this and in using look-ahead strategies in order to exploit our relaxed plans, we realized that we could improve the YASP look-ahead strategy. So even for those who may not find our heuristic interesting, this might be interesting for you if you like using look-aheads. And fourth, we have an experimental evaluation showing that this actually works. So the background, I'll be going over the rest of the talk on the background and treating relaxed plans as optimization, as I told you, how we compute this, our new look-ahead strategy, and the experiments. And okay, series planning, I don't think I need to go over this. The only thing we use actually that may not be that standard, we refer to prevailed facts by actions. This may be more standard for SAS planning. So the prevailed facts by an action are those preconditions that are maintained by the action, that are not deleted by the action. And we use this regression operator, which is basically just telling you the conditions under which you will achieve the goal after performing an action. Okay? That's pretty standard, too. Okay, so vanilla relaxed plan computation. This is by this I'm actually referring to what FF does. Very simple. Just quickly, we expand the relaxed planning graph in which deletes are ignored, no mutexes. And then from there we extract a plan by regressing the goals, and we select the goals that were achieved later. Start iterating from the back, and we prefer cheap achievers. So that's really simple. And now I'm going to show you how we actually treat the problem of relaxed plan as optimization. And this is sort of the motivation. I'll go back to this example to motivate the thing. So it actually turns out that the bad thing about using relaxed plan in plans in this domain is that the relaxed plan for this just tells you to put the crates, both C1 and C2. Here's 2 crates, okay? So you put them both in the same location, A4, and that's very bad, because if you take into account the helpful actions, those actions that will help you, are supposed to be the ones that help you toward finding a quick solution. You find out that the only action that actually helps you in solving the problem is not there. Actually, to solve the problem, you have to get into the depot and then drop something inside. Here, you can't go this way. So always, the only way to get in is to put the crate in. By the way, I may have forgotten to say that only one crate can be in a location. Okay. So the only action that is useful here, you can't actually, you don't have it in your relaxed plan, and you don't have it as a helpful action. So the notion of conflict we will introduce will actually reflect the fact that there's something wrong in the relaxed plan. And we will say, for example, that there's a conflict between these 2 actions, or there's a conflict that arises by considering these 2 actions. Our relaxed plans are constructed by then attempting to minimize those things. So I'll now define what a conflict is, which is now like the big mystery of the whole thing. So the conflicts are going to be based on mutexes. So that's nothing new. Here we say a permanent mutex is just a set of facts that can be both, but can be all true in any reachable state from the initial state. And the first type of conflict we introduce is the delete conflict. For people who are used to regression planner, this is exactly what you never want to do while you do regression. You never want to delete a goal that's currently in the set of goals you want to satisfy. So we say that an action A produces and deletes conflicts if the set of facts that are deleted, if the set of goals that are deleted by the action that you're currently adding to your relaxed plan is N. Remember that we are constructing the relaxed plan from the end. So this G is it's going to be actually the set of goals that are currently in the that we're currently trying to satisfy. Okay. On the other hand, we have these add prevail conflicts, which end up being also very useful to produce better relaxed plans. The intuition basically here is that if you have a current set of goals that you're trying to satisfy, and it turns out that your action maintains certain facts that are in conflict with the current goals, then that action could not happen at that moment if you were planning in the real world, right? But since we're constructing relaxed plans that are going to minimize conflicts, we count the number of these and we try to minimize them. Okay? Then that's the add prevail. And precondition conflicts are actually a bit similar to these. The precondition conflicts are those conflicts that will be produced like after regressing the goals through the actions. So there could be preconditions in the actions that are not the ones that are prevailed actually, and that are in conflicts with the goals that will be active like after regressing the current set of goals through the action. Okay? Oh, that's clear. So just an example to make this clear. So this is the relaxed plan that we were looking at, and the example. The relaxed plan considers putting both crates in the same location, and there's going to be a conflict here, and the conflict is the type of delete conflict. So the red action will be in conflict with something that was generated by the drop action. And actually, it happens that the drop action here, which drops the crate 1 in location 4, A4 from the hull, deletes a precondition of the drop of the previous meaning the one that it's in the end of the drop that puts actually the crate in the same location. Okay, so that will be considered as a conflict. And now the objective of the algorithm would be to try to construct something that tries to avoid this somehow. Okay, okay. So the problem, maybe it's already clear at the moment. Formally, it's this given a planning problem. The optimization problem is to minimize the function conflict that operates over a relaxed plan. It counts the number of conflicts that are achieved as you regress the goals by each action. So it will basically count the number of conflicts that are added by each action in the relaxed plan. Okay? So now we want to solve this optimization problem. And before solving it, we may notice that most of you have noticed already that if we actually solve this optimization problem exactly, we end up with a plan. And that's something that is not easy, not that hard to prove. It's quite easy to prove. So we are not going to aim at solving this problem exactly, obviously, and we are actually just want to use this for heuristics. So we're obviously not going to find an exact solution. And what we decided to do here was to try to adapt the current algorithm for extracting conflicts in such a way that you would, the current algorithm for extracting relaxed plan, which is the EFF algorithm, basically, so that it will consider conflicts while extracting the relaxed plan. There are many details that I don't have time to go over with, but this is the main idea. The thing that is in blue are the things that are different from the FF algorithm. Everything else is kind of the same. So we also start building a relaxed graph, and we select the goals. And instead of starting from the end and selecting just a goal that has been achieved at the very end layer, we just choose a goal that can be achieved with the fewest conflicts. Okay, so in that way we're being greedy. We're seeing all the achievers, and we're choosing the first, the one that it's achieved with fewer conflicts. Then after we do that, for example, we select the cheapest achiever in the same way that cheap is defined in the FF algorithm. And then after choosing the action that produces the fewest conflicts, this action actually may not produce zero conflicts. There might still actions that, the action that we chose still might produce conflicts. And in that case, we try to do two things. The first thing is what we call this conflict avoidance, which could be seen as a limited backtracking. So we're not going to try to solve this efficiently, but we're going to do some kind of backtracking. And the limited backtracking reflects in the way that we try to change an action at the start of the current RP. So basically that says that you are allowed to backtrack, but only to the previous action. Okay? And on the other hand, if after doing that we can't do anything, or we can't do much, and action A still introduces conflicts, we try to repair the conflicts that are introduced by this action by adding a chunk of actions in between the current relaxed plan and the action that we're going to add. Okay? The justification for that is, I think I don't have time to go over that. But people who are familiar with partial order planning may find this thing not that absurd. Okay, so what's an example of how the algorithm works? Well, I don't have a full example, only a little example. So here, just assume that in your current relaxed plan suffix, you have the action drop the crate in this position. Okay, what will happen now is that the next goal will be to achieve C2 in depot 1. So maybe I want to achieve that this one is here. Okay, and if you go from the back, you will find that our algorithm, in this case, and this is an exact run actually, by assuming that this is the case, will find this action. So instead of putting the crate here, it tries to minimize the conflicts, and in doing so, it decides to put it in another position. Okay. But after doing that, there are still conflicts. And in this case, as I told you, there's one phase which will try to do a simplified backtracking. We'll try to change this action. And in this case, it is possible. So by changing this action, the algorithm does realize that you can actually reduce the conflicts. And it will actually replace the action drop the crate in A4 from the hole. And it will decide to do this. And although we had already an action that looked to be okay, because it was not putting the crate directly inside in the same position, was not putting the crate here, which was the original problem. Here, in attempting to minimize the conflicts, we chose to basically drop the crates from the same place. And the reason why that is done is because these two actions are still in conflict, basically because they assume that the crate should be in a different position. And being in two different positions at the same time is clearly a conflict. Okay? So that's sort of the idea of the algorithm. After running this to completion, you'll find that this is the plan. And the very important thing is that by not choosing to put everything here, this action comes into the relax plan, and that means that this will be a helpful action, and that seems to be pretty good in this domain. And we'll see in the experimental results that this domain turns out very positive for our technique. So the other thing I told you is that we proposed a technique for look ahead. A new technique for look ahead. And just a quick overview, I'll have to assume that you have some knowledge in look ahead strategies. So ICAPS is this planner that uses look ahead. The idea is basically that you can go further in the search space by not just applying one action, but many. And the many actions are taken from the relax plan. So you take the relax plan of a state, you try to perform as many actions as possible, and once you've done all you can do, perform all the actions executable, you will try to perform those that have failed already, and that's denoted by this failed here. Okay, and you will try to find a repair in that sequence of actions that failed, and the repair is basically an action that could replace a current action there, and that adds an effect of the action that was already failed. So basically, it's just going over the sequence of failed actions and try to repair one of them, so that you'll do something similar to what an action to what the action was doing originally. Okay, and this repeats until you can't do anymore. So Vidal showed that look ahead increases coverage significantly, allows you to scale, but this is at the expense of quality. Okay, plan quality. Okay, so our new look ahead heuristic is based on Vidal's look ahead, and it's very similar, but changes something important. So first we perform as many actions as possible, just like ICAPS does, and then we end up with this chunk of actions that couldn't be performed. And now what you're going to do is treat this chunk of actions as if it were a macro actions. Okay? And if you treat this as a macro action, you can compute the preconditions of this macro. Okay? And what you will do here is we'll try to insert one action before this macro such that it will try to achieve the maximum number of preconditions of this macro. Okay? So you compute the preconditions of failed, and then you try to find an action that maximizes this difference. The preconditions that are added by the actions minus the ones that are the preconditions that are deleted by the action that you are adding. Okay? And that will repeat until there's nothing more to execute. Okay? So that's the idea, very simple. Okay, so we decided to evaluate this. The evaluation is over 19 planning benchmarks. The time limit is 15 minutes. That's the other data. Okay. Okay, so the planners we decided to evaluate, and actually many of them. So we decided to extend FF. The reason is basically we wanted to compare it exactly to the FF heuristic. We extended FF with look-aheads. So we implemented ICAPS look-ahead and our look-ahead. And then we compared to our heuristic with different values of K. And K, I didn't stop on that. K is the number of actions that you use for this repair that you could insert in your relax plan. Okay? So we tried actually all these combinations. Okay? We executed them all. And to compute the mutexes, we used the H2 heuristic. So we only restrict here in our implementation to binary mutexes. Okay? And that's only done at the beginning of the search. Okay. So then we tried this FF also extended using the FF heuristic. And we compare also to IASP and to Lemma. In the end, it turned out that this configuration was the best. And overall, that doesn't mean that this case doesn't help. I can comment on that afterwards. So the table that we're going to see is actually comparing our heuristic with the FF heuristic using the same look-ahead, which is, by the way, our look-ahead. So here's something, yeah, the colors don't seem to show. So just focus on the first line. This shows the state expansions. And higher numbers are good for us. So this means that our heuristic was more informative in these cases, not more informative in these other cases. Although it's a lot more informative in some cases, there's a cost we pay in length. Okay. Okay. Solutions. In terms of coverage, we're doing better. By the way, this is only a selection. There are more domains in the paper, but the average over all the domains we tried is better. And if you compare against YASP and Llama, we also get reasonable results. Okay, so our heuristic is slower to compute, but if you take a look at how many instances we solve, these are our planners, and this is the FF planner with look ahead. It turns out that if you only give our planner 30 seconds or more, it solves more instances than the other ones, than the planner that uses the FF heuristic. Okay, so this is the number of problems solved, and this is search time. Okay. Okay, is our heuristic more informative? We tried using only enforced climbing and not look-aheads. And there, the benefits still show, but not that much. And the reason is that, well, we're not exploiting all the content of the relaxed plans if we only use the helpful actions. I can go over this afterwards. And is our look-ahead better than the previous one? And the short answer is yes. In 9 domains, we solve more problems. And in no domain, we solve fewer problems. And the quality only gets degraded in 1%. Okay. So summarizing, the motivation was to investigate the effectiveness of not so relaxed relaxed plans. We defined this optimization problem that we attempt to solve with the greedy algorithm. We define a new look-ahead strategy, and our experimental evaluation shows that this is something promising. The message of the talk is basically we can do better if we consider deletes, and in the way we did it with conflicts. But there's more things to investigate. The algorithm we use in particular may be very probably not very nice. I think there are more things to do. It turns out that if you consider fewer conflicts, you may get better. It's something we are actually investigating. And there's some related work I don't have time to go over. That's all. Thank you. Carmel is behind. Yeah, yeah. That if you solve the problem to you.
Now, the proposition that appears there does not imply that. The proposition that appears there says that if the optimal value is 0,
Yeah.
then in this particular case, the
Yeah.
value defined is also correct. But that does not imply.
It's true. It's true, and it will be 0 if there is a relaxed plan that minimizes the conflicts. Yeah. So that basically means that there's a solution. So. Right.
For this particular fragment of planning problems, planning is easy.
You mean the ones that the
That, for example, appear in problems for which
okay.
there are plans. Well, I don't
Oh, okay.
know but just be careful with claims. Problems for which there is a valid plan within the H-max horizon of the planning graph.
Oh, no. So the proposition only refers to any relaxed plan, not to the ones we are restricting to. No. Yeah. It's rather trivial. That's why I said it was. Yeah. I think it's the. Thanks for the question. I think the best intuition is that in some domains we got better results. Like for example, in domains in transportation domains, actually it turns out that in logistics you find an exact solution almost if you use k equals 1. But increasing this value for other, for example, transportation domains where you probably would need to, go through several locations to get to another one, makes our particular implementation very slow. And that ends up not paying off in the long run, although it may be more informative, doesn't it? Mm-hmm. Oh.
I was curious about how your heuristic compares to this. It almost seems like you're just running
Um, Yeah, so that's a good question. Actually, one of the things I wanted to do before using the solution I proposed was actually to use LPG. So there is a relationship. I thought that I mean I tried LPG. I couldn't penetrate it, the code. So but yeah, so there is some relation between these two things. Yeah. And that's something I say investigate other optimization algorithms, and I mean, well, trying. I think those things are interesting and related. Yeah.
Hi, hi. Yeah, it works.